So welcome everyone. It's quite a sizable audience for a database benchmark talk on a Sunday afternoon. My name is Gábor Szárnyas, and in the following 30 minutes I will talk about database benchmarks and what I learned about them while running a benchmark standard organization. A little bit about me. I spent a decade in academia, then I was building up a benchmark nonprofit called the LDBC, and now I work at a database vendor. An overarching theme of my career is doing database benchmarks and using them. Today I'm here in my benchmark nonprofit hat, and I will try to share the lessons that I learned as such. The talk has 5 parts. I will talk about the need for database benchmarks, then I will talk about 2 benchmark organizations, the TPC and the LDBC. Then I will review some popular benchmarks in modern times, and I will leave you with a bunch of takeaways. So let's get started. Why would you benchmark databases in the first place? It turns out that databases and benchmarks are a pretty good match. First of all, users usually care about performance. They spend a lot of time optimizing their workloads, and if the database can do this for them, or if the database allows them to go further, they are quite happy about that. So the vendors are incentivized to have good performance, or at least to claim good performance. Databases are also mostly deterministic. Benchmarking a database seems reasonably straightforward because you get usually the same query plan and some similar execution time. So it's not like benchmarking a large language model, which is a lot more stochastic than a database. So at this point, you may expect that you have a data set, you define a bunch of queries, you throw it at the database, and then you write down the numbers of the database's performance, and this will somehow magically make database benchmarks work. Unfortunately, reality is a bit more complicated than this. If you just do dataset and queries, you will not really stress updates in the database, which is a crucial part of any database system. If you just run the same queries over and over again, you get a limited understanding of how the optimizer works. So you should also plug in different parameters into those queries. And you need to somehow tie all this together into a workload definition. The database is, of course, a piece of software that doesn't exist in isolation. You have all these layers under the database: the file system, the operating system, hardware, network components, maybe a container, an emulator, some virtualization layer. These all have interplays with each other that can have an effect on your results. And finally, performance is important, but correctness is also important. You have to verify that the results are correct. And usually pricing is something that users deeply care about, so you need to assess the pricing of the system. And speaking of being deterministic, yes, databases are mostly deterministic, but reproducibility is still difficult. It's quite difficult to hit reliably the same code path in a database system. And you have all these extremes of different runs, cold runs, which are incredibly difficult to do because you basically have to restart the computer, restart the database, and then run the query to get a true cold run. And hot runs, which are easier to achieve because you just run the same thing in a loop, but maybe they are not that relevant. So when you're measuring systems, you are kind of in between lukewarm and warm runs in a system, and there can be orders of magnitude differences between these runs. Another surprisingly difficult thing is that once you have done your benchmarking and you maybe have 100 million little entries in your benchmark report, you would need to write them up in some sort of a summary aggregate statistics. And there's an excellent paper from Thorsten Höfler and Roberto Belli where they explain how to report these in a parallel computing system, which is, of course, every computing system these days. And I cherry-picked 2 rules for you. Rule 3 says that you should only use arithmetic mean, the average, for summarizing costs. If you are summarizing rates, like transactions per second, you should use harmonic means. And if you are summarizing ratios, first of all, you shouldn't. You should go back and dig out the original values from the base data and then summarize that. But if you only have these ratios or speedups available, then you should use the geometric mean. So we basically use all the Pythagorean means just to report on some sort of an average in terms of costs and execution. Another thing is what to measure. Micro-benchmarks are quite popular in research. You measure one join operator or maybe just a simple hash probing. This is very interesting if you're implementing that operator, but for users, it's more interesting to have macro benchmarks, load the data and run a bunch of queries, or even application level benchmarks that measure the database system's performance end-to-end with complex updates, with maybe a more intertwined workload. So this is all quite difficult even if you have the best intentions. But let me tell you, in the 1980s, database vendors did not have the best intentions. In this period, relational databases were still kind of immature and had major performance problems, and something called benchmarking was quite common. This means that benchmarks were misused. Vendors were even implementing their own benchmarks, and surprisingly, they won their own benchmarks, and then they boasted about these results. An interesting chapter in this story is 1982, where Professor David Dewitt measured a bunch of database systems, including Oracle. He published those results, and that didn't really make Oracle happy, so they put a clause into their license saying you are not allowed to publish results unless they are officially sanctioned by the company. And this became so popular that this is called the Dewitt Clause based on this little event. But by the end of the 1980s, it was kind of clear that everyone doing their own benchmark is not really doing any good, and there is a clear need for an independent authority and the benchmark standard. And thus the TPC was born. The TPC, somewhat confusingly, stands for Transaction Processing Performance Council. This is a non-profit company that is based in the United States, and it was founded in 1988 with the mission to make standards for benchmarks and then to make official results for those standards available. TPC's membership has fluctuated over the years. At its peak, it was around 40 members. Now it's at 21 members, and you can see it's heavily dominated by companies based in the United States and in China. With regards to the type of companies that are members, that's also worth mentioning. You have the hardware vendors like NVIDIA, AMD, and Intel. You have these server building companies like Lenovo, Dell, and HPE, and you have cloud vendors, you have database vendors, so it's kind of an interesting mix of companies. And what do? I picked TPCH because this is their most influential and most popular benchmark as a good example. TPCH was released in 1999, and it captures an ad hoc analytical workload for a wholesale supplier. If you look at the schema, you have a supplier, you have parts up, you have line items for the entities that you are selling, and you have 22 queries that do analytics over these tables. It also has some refresh operators for inserting and deleting new data. The pillar of TPCH is the data generator. The data generator can create data sets in different scale factors. A scale factor is defined as the size of the data set in gigabytes. So when we say scale factor 100, we mean it's 100 gigabytes of data. This is actually a really good way to measure it because CSV files are kind of timeless. It's really easy to understand that it's a plain text serialization. And even though these days we are mostly using binary formats, this is still very easy to understand. The original data generator was written more than 25 years ago, so it's written in C and it's not thread safe. But luckily, a bunch of people last year rewrote it in Rust, and you can now just pip install it and run it basically anywhere through Python. And this is a really neat piece of software, and I think this is worth mentioning because if you ever need like 100 gigabytes of data at your disposal on your laptop, you can just run these two commands and it will produce a somewhat meaningful data set in less than a minute. So this is even interesting if you're not into database benchmarking per se. The queries of TPC are obviously quite involved. I don't have time to go through all of them, but here is a really interesting example, TPCH query 1. This is a rather simple query. It uses a single table line item, it uses some simple filtering, and it uses a bunch of simple aggregates like sum, average, and count. And I like this query because this is something that realistically every analytical database should be good at. It doesn't have anything complex. You can implement it as a benchmark query in maybe a few minutes. And if you just start out building an analytical database system, you can start benchmarking it with this query quite early on in your journey of building the system. The way TPC benchmarks works is that it has three distinct phases. You first load the data to your database. Then you do something called a power test. The power test means that you take the 22 queries and the refresh operators and run them sequentially. This allows you to measure whether the database can do inter-query parallelism, whether it can exploit multiple cores for the same query. Then you compute the geometric mean runtime of these queries, and you get a power score. Next up is the throughput test. This is concurrent. You run queries and updates concurrently and try to achieve maximum throughput. And then finally, these are put together in a composite metric by taking a geometric mean of the two. And this weirdly named metric, QPHH, is something that we used to track the performance of analytical workloads. I dug this out of the official TPC results, and it actually shows a really nice trend line starting from 2001 until 2020. And what you can see is that basically the trend line starts around 5,000 QPHH points, and now it's above 5 million. So this is 1,000x or 41% year-on-year improvement in terms of analytical performance that is at your disposal when you buy a state-of-the-art database system. TPCH has been so influential that people try to do some reverse engineering on it and break it down on, first of all, why it is such an efficient benchmark, and second of all, how you should excel on it if you're a database vendor. So if you read this paper, it defines these choke points, these kind of well-defined bits of difficulty that the benchmark encodes, and you can see how the improvements on those choke points would improve your results on TPCH. So, for example, if you improve aggregation, it will have an effect on all of the queries and the more outsized effect on some of the queries. If you improve joint performance, you will not impact queries 1 and 6, but you will deeply impact queries 9 and 18. Another benchmark from TPC is TPCDS, and I brought this more of as a cautionary tale. This is a more modern and improved version of TPCH, so it's for analytics. It models a retail product supplier with multiple sales channels. It has dimension tables, fact tables, and it's more realistic than TPCH in general. The problem with TPCDS is that it has 99 queries, and on average, they are almost 2,000 characters per query. So that's 200,000 characters almost just for the query definitions. The deletes are also more complex. You have these cascading deletes from one table to another. If you delete something from sales, it will scatter into the returns fact table, so they are more difficult to implement efficiently. As a result, even though TPCDS was released in 2011, the first audit took 7 years for someone to overtake. It was done by Cisco, and it was the scale factor 10,000 result. In the next year since, there was a scale factor 100,000 result by Alibaba, and in 2021, there was a record-breaking result on TPCDS by Databricks on the 100,000 scale factor. This actually triggered a subsequent benchmark war with Snowflake, with Databricks and Snowflake putting out press releases, blog posts, and social media on why their system is better, more efficient, and better in terms of price performance. This is a really interesting read, and I'm also happy to chat about this after the talk. So I said that TPC acts as an independent authority, and they have official results. The way you achieve it is that they have an auditing process that you have to undertake. If you want to audit your database, then you become a test sponsor and you commission this audit from the TPC. You have to run the experiment yourself, and you have to write it up in the full disclosure report yourself, and then you hand it over to a certified TPC auditor who validates the result. They have pretty high powers. They can not only rerun your experiments, but they can do additional checks. Back in the day, they could fly to your server farm and plug the server out of the socket to see whether the durability of the server is really there. And they do all sorts of these checks to make sure that there are no benchmark specials in your system. What is a benchmark special? Well, vendors are incentivized to do well on TPC benchmarks, so sometimes they build in operators just to do a TPC query well. And the way the auditors try to catch this is, for example, by garbling some of the queries. So this is query 1, and this is query 1 with all the column names and all the table names replaced with some random encoding. This prevents systems from using hard-coded, highly optimized operators and query plans if they use this method of detecting which TPC query is running. An important part of TPC benchmarks is pricing. TPC pricing is a specification that's almost 70 pages, and it captures how you should price the total cost of ownership for a given database system. And this has three major components. The first is a software license, which can be zero if it's free and open source. The 3-year cost for the hardware and the cloud service if you use a cloud vendor. And then you have a 3-year maintenance with enterprise-grade support. Now, I personally have two main criticisms with this pricing. The first of all is that I believe the enterprise support is very strict. It's quite common, especially in analytics, to run database systems without 24/7 enterprise support. So more of a next business day support would be sufficient, and it would keep the prices more realistic. But my bigger problem is that this is really an outdated way of thinking about databases. People who run databases in the cloud where the storage and compute are disaggregated, and you can elastically scale the compute depending on your needs, don't rent out computers for a fixed 3-year period. And you can actually see the effect of this in the pricings that are reported. For example, the Databricks audit that I have mentioned from 5 years ago, they run it on 256 machines, and because of this, the TPC pricing specification just assumes that you would rent this out for a 3-year period, and this yields a hefty sum of $5.2 million. This is obviously not a realistic number for doing data processing on 100 terabytes. 100 terabytes is not that much in these days. One interesting thing that I noticed is that I plotted out the TPC number of audits in the last 15 years or so, and they have a moderate negative correlation with the US federal funds interest rates. This is because the closer we are to zero interest rates, the more money is available for venture capital investments. And when there is money in the VC market, the vendors are rushing to get TPC audits and try to one-up each other in terms of performance in the hope of getting more venture capital. So that's kind of an interesting observation, but of course, it's not the full picture. All right, so we arrived to LDBC. What is LDBC? Well, it is a non-profit founded in 2013, registered in the UK, and its goal is to accelerate progress in graph data management by facilitating this sort of pro-competitive work, where you collaborate on standards and then try to be the best one at implementing that standard. The name LDBC reflects this focus on RDF processing back in 2013, so it's the Linked Data Benchmark Council. Back in 2011, when the idea of LDBC came up, it was very similar to the 1980s of relational databases. Graph databases had major performance issues. There was also no standard graph query language, and there was just no common understanding of what a graph database system should do. So some vendors and academics got together and created this organization. Today, in 2026, we have 18 members. You can see that, again, it's dominated by companies based in the United States and China. And we also have cloud vendors, we have software vendors, database vendors, and consultancy companies. LDBC is heavily inspired by TPC. So we do complex application-level database benchmarks. We define data generators that can do different scale factors up to tens of thousands of terabytes. And we designed our benchmarks even based on the TPCH choke point methodology. So we took the TPCH choke points, we extended them with graph-specific choke points, and then we made the benchmarks such that they cover these choke points. We have a stringent auditing process, and we have adopted the TPC pricing specification. Let's take a look at our most popular benchmark, the social network benchmark. This uses a data set that's capturing the Facebook data set in terms of distribution and in terms of the number of edges a given person has. It's actually based on a 2011 paper. Of course, we not only have people in this network, we also have the content that they create. This is in the form of messages, and this forms this nice graph where the left side is a network and the right side is a bunch of trees. So what can we do in this? A very simple simplified example query is this. We have two parameters, a name and a day. And what we're interested in is that starting from a person with a given name, if we do 2 hops along the nose edges, friends and friends of friends, and then we check the messages that those persons authored, what are the messages that were created before a given day? So let's go through this with an example. Let's say we are interested in Ben and messages before Saturday. In this case, we do 1 jump along the nose edges to get to Ada and Carl, 1 more to get to Finn, Eve, and Dan. Then we hop over to these messages, and we get a filtering operation to get the ones that were created before Saturday. So visually, it's all very simple, but for the database, it means efficient lookups, joins, filtering. So it's quite an involved operation. And of course, updates are also interesting, and in the graph space, this is even more so. We can do simple inserts. That's not that special. We just add a nose edge between Eve and Gia, or we decide that Gia is creating a reply to message M3 on Sunday. This is pretty run-of-the-mill stuff. But where graph databases can be interesting is when it comes to deep delete operations. So, for example, if we decide to delete the person Eve, then that could be only deleting the node and the outgoing edges. But if you are privacy conscious and you need to delete all the data that that person ever created, that also means removing all the comments that she ever wrote and maybe the replies to those comments and the likes to those replies. So it can be kind of a rippling effect, and we just removed 1 node and ended up missing almost half our example graphs. So deletes in graphs are quite heavy-hitting operations. How does this all add up into a benchmark workload? Well, we have a pre-processing phase where you can tweak the data to your liking, then you load it into your database, do a 30-minute warm-up, and then a 2-hour benchmark run. The goal of having this 2.5-hour period is to have some realistic representation of an actual live system where the database is running for a prolonged period of time and not just running a bunch of queries. The workload mix composes of 3 different types of operators. We have complex reads, like the one I have shown you. We have short reads, like looking up a certain message or getting the friends of another person. And then we have the update operators, the inserts, and the deletes. And the way we replay this is actually quite interesting. So in the generator, we simulate a 3-year period of the social network's activity. We write down the timestamps, and then we replay them. We try to compress time based on something called the total compression ratio. So for example, we have 4 operators here along some logical simulation time. And then if we have 2 threads to run the benchmark, we can compress them by putting updates 1 and 2 on thread 1 and update 3s on thread 2. It's actually more involved than this because there are all sorts of data dependencies. For example, you cannot like a message before a message was created. So those have to be tracked by the benchmark driver. But once you're done with the tracking, you can do the scheduling. And then we schedule everything else to follow these update operations. For example, we do maybe 10 updates between each query 1, 15 updates between each query 2, and so on. And then the queries themselves also send off kind of a short read ripple. This is to simulate that you have written a message, but now you're maybe looking around in the social network to have something more to do. If you start running an actual database and start to hit it with this workload, what you will notice after some time is that maybe the database is not able to keep up with your workload. So the start times of the queries will start drifting back in time. And obviously this is not great. What we want is that the database should be able to keep up. So we have this on-time requirement that 95% of the executed queries must start within 1 second of their scheduled time. Otherwise, it's an invalid run. All right, so we have the data set, the queries, the updates, and the workload mix. How do we do audits? Well, as I said, we have strict auditing guidelines similar to TPC. We have a list of certified auditors that you can work with. And unlike TPC, here the auditors are always rerunning the benchmarks, and they are writing the full disclosure report with all the details. One sign of success that we have noticed a few years ago is that people told us that they have seen these RFPs, requests for proposals, for internal procurements in companies that necessitated official LDBC benchmark results. So as a benchmark organization, you sometimes get to become the arbitrator of whether a system gets picked or whether another system gets picked. You can see a list of audited results on our webpage. And just to create a similar plot to the CPCH plot, here is how our transactional workload ran on scale factor 300, the 300 GB dataset, over the last 5 or 6 years. What you can see is that it started from around 4,000 operations per second, and it grew to about 30x to more than 130,000 operations per second. What you can also see is that these are all vendors based in China. Apparently, China has a very healthy venture capital ecosystem for funding projects like this, and these companies were basically one-upping each other in terms of performance. So this kind of driving competition thing really works with benchmarks. We did quite a few audits, so I have a few lessons to share about this. One thing that we have noticed is that performance variability is huge, especially in the cloud. We had issues because of limited disk space. We had issues that you get a different machine and the performance of the I/O is widely different. But we also had issues where it was a machine that was good, there was enough space on the disk, but on the second run it just had an inexplicable performance drop. This is obviously something that the auditor needs to take into account. We also noticed that sometimes there were misaligned expectations because the vendors expected the auditor to finish the implementation. And in general, the audits always took much longer than expected, sometimes 3 or 4 months. We try to mitigate this by having an elaborate questionnaire of dozens of questions that we do during the pre-auditing process, but this is still a difficult challenge to get the audits done on time. A few words about organization. So obviously, running such an operation will need some sort of an organizational structure, some sort of financing, and so on. LDBC had 4 distinct phases in its lifespan. It was originally an EU project with almost 3 million euros of funding. Then it coasted for a few years, mostly living off of favors of vendors and academic institutes. Then we actually started collecting money from our members, maybe $2,000 from regular members. So we had small fees. And from last year, we upped this, and now we have a healthy 150,000 euro per year income. This looks nice, but it actually has quite a few problems. And the problem is banking. We were kind of doing rounds at different banks and ended up settling on one of these new fintech neobanks that you use from your phone. Neobank 1 kicked us out without explanation. We were moving our funds to Neobank 2, and they blocked our account, and they triggered an urgent and extensive KYC, Know Your Customer check, because they said we have an unusual structure. Or they didn't say that, but the reason was clearly this. And of course, what this means is that they really don't like organizations that have 25 directors from more than 10 different companies. So we passed this check, but then we did a restructuring of the organization, and we were happy for a few years until they said, oh, we cannot accept money from your member X. In the last couple of weeks, I tried to migrate to Neobank 3. They denied our application straight away. So you can see it's kind of difficult to do. Maybe we will go to London into a traditional brick and mortar bank and open an actual account with an actual person instead of fighting support. That is to be seen. So it is a difficult thing to run a benchmark organization, and it's also difficult to have a value proposition. We found that vendors join us to have a seat at the table when the benchmarks are designed. And one particularly interesting reason is the defensive reason. They want to prevent the benchmarks to be used against them. So they are there to prevent a new benchmark being defined that puts them at a competitive disadvantage. Interestingly, many of our vendors say, yes, benchmarks were nice. They have maybe achieved their goals, but now you should focus more on query languages, graph schema, and de-emphasize the benchmarking part and just keep some data sets and synthetic data generators. To reflect this, LDBC has actually rebranded as GDC, so we are now called the Graph Data Council, and we still do benchmarks, but it's more kind of a overarching theme on graphs instead of just a benchmark organization. All right, popular benchmarks. I have two popular benchmarks to talk about. One is ClickBench. This is something that's a macro benchmark for analytical database systems. This is something that's designed and maintained by ClickHouse, and this is designed to be an easy-to-use benchmark for analytical workloads. The dataset has a single white table of about 100 million rows and 105 attributes, so 10 billion plus cells in the table. It's 75 gigabytes in CSV, and it's web analytics coming from the Yandex Metrica dataset. The queries focus on scan operations, aggregations, and lookups. You can see a bunch of queries, starting from the simple COMSTAR, through some filtering, through more group by aggregate queries. ClickBench's philosophy, as much as I can tell, is to strive for simplicity. So there are no scale factors, no query parameters, only simple type, and very few restrictions on the implementation. And the whole benchmark is kind of fast-paced, and you should be able to do a git clone, go to your directory, do the benchmark, and finish within 20 minutes, including downloading the dataset. And then you can open a pull request, and they usually review it within a few days. This allowed ClickBench to scale up in terms of the results quite quickly. They have more than 75 different systems with 125 different configurations. And I think this is a massive success in terms of stimulating competition and just getting people their results out there. They have somewhat standardized hardware, so there are a few common setups that are at the center of the competition, but you're welcome to bring your own setup, maybe on-premises, laptop, GPU, you name it. If you open ClickBench, they have this elaborate leaderboard, and if you zoom in, it allows you to compare systems. I picked MySQL and Postgres because none of them has a reasonable chance of being good on a fully analytical benchmark. And you can see that you can compare their performance, you can compare their system sizes, the database size, that is the size after loading, the load times, the individual query run times, and so on. Another benchmark that is reasonably popular is called H2O.ai. This was originally created by Jan Goretzky and funded by H2O.ai. Then it was abandoned, and now a fork is maintained by DuckDB Labs, where I work during my day job. It has two workloads focusing on group bys and joins, and three scale factors, 0.5, 5, and 50 gigabytes. You may have seen it floating around on social media. It has these really recognizable colorful squares and these long bars representing the first runtime for the cold run and the second runtime for the warm run. This is a synthetic data generator, and the workloads themselves are really simple. So 5 basic groupings, 5 advanced groupings, switching between low and high cardinality, grouping on different types of strings, and so on. And there is a join workload with 5 different join queries. We are the maintainers of this benchmark, and we keep getting proposals for extending it with different functionality like window functions. This is actually becoming a dilemma for us. What do we do with it? If we keep as it is, then it's slowly going to become a stale benchmark. If we extend, then people will say, well, you just accept the proposals that make your system look good. Again, an independent benchmark authority would be nice. It's kind of difficult to maintain a benchmark as a vendor. So to kind of round it out, the takeaways. I think benchmarks do carry tremendous value. They capture a common understanding of your field. They drive innovation, but they are difficult to finance. And even though vendors use them extensively, a lot of that is internal use and is difficult to get funding for it. Here's my ideal benchmark in one slide. If you ever do that, maybe it's worth visiting. And I would just like to leave with the fact that you maybe shouldn't build your own benchmark organization from scratch. LDBC or GDC is open. Please reach out if you would like to learn more. Thank you.